So the first question is, what type of grounding do most data centers use?
On the higher end of data centers, most of them will use either solidly grounded or high resistance grounding. We're seeing that with certain high level companies that are building new data centers at the moment, is that on the top line, where the incoming power is coming in from the grid connections, they're utilizing high resistance grounding at that point. But when it gets down to the PDU racks where they need that fourth wire or a concentric neutral, they may switch that system to a solidly grounded system because they have single phase loads to satisfy. So on the upper level, they will have on their three-phase three-wire setups high resistance grounding, and then when they need the neutral, they will introduce an isolation transformer and then convert that system to solidly grounded. Now, in that case, they may have to trip right away when the PDU rack is experiencing a fault of any type, but at least their upstream system is not impacted by that fault coming from the solidly grounded system, and then they can still maintain process continuity on their three-phase three-wire setup. In the case of data centers, time is definitely money, especially when it comes to data and making sure that it's readily available. So banks and technology companies that even a minute or an hour of downtime could impact their revenue greatly by millions or even billions of dollars.
Why does an NGR require two sets of CT sensor?
Two sets of CT sensors may be required because for, let's say, a generator application, you may have an SEL 700G or another generator-based controller from GE, like a multi-lin. And in that case, that generator controller may be doing some overcurrent protection along the neutral or ground fault pickup that may be auxiliary. The second CT has to be utilized particularly for our resistor monitoring. Now, the resistor monitoring is a new code requirement, especially for us in Canada. In the US, this code requirement does not exist yet, so you may only be picking up for ground fault. But having resistor monitoring is a nice to have just because we're able to detect the open circuit scenario and short circuit scenario. The reason why that's important is because the neutral grounding resistor is essentially your only system ground connection. If an open circuit occurs, then your system becomes ungrounded and your entire system's floating. Conversely, if your system gets an NGR short circuit, then your system will behave as a solidly grounded system, and you're no longer limiting that fault current to a very specific value. And you're basically exposing yourself to arc flash potentials since we're no longer limiting that fault current.
What's the advantage of using a low resistance grounding instead of high resistance grounding? In which scenario do I use it?
So for systems that are 480 volts, 600 volts, the standard is to use high resistance grounding with either a 5 amp or 10 amp NGR. The reason being is that for Canadian customers in table 17, if your system is three-phase three-wire, you're using a continuous rated resistor. And if you're limiting fault current to a 10 amps or less using either a 5 amp or 10 amp resistor, you have the ability to alarm the condition of ground fault without having to trip the system. So a lot of customers are utilizing that at the moment to provide process continuity for systems that are 5 kV and below. As you get to systems that are greater than 5 kV, you would need to consider low resistance grounding, where you would coordinate with your fault protection scheme at the feeder level to basically limit the fault current to a more specific value to reduce incident energy levels, and then coordinate with your downstream pickup values for ground fault that are coming off of your either sensitive relays or the G function of the breaker if you're utilizing that still. I know majority of the consultants are now focusing on third-party relays for their feeder protection on systems that are greater than 5 kV. And in that case, we would just have to look at what the ground fault pickup settings are and size the NGR's let through current in accordance to that pickup and trip on first fault.
How does the system work in power systems with a standby generator?
So for standby generators, we would have to look at the single line diagram specifically to see how it interfaces with the normal power. If that standby generator is simply kicking in after the normal power has, let's say, been compromised, through some sort of switching method via Kirky interlock or ATS, then we will basically apply a neutral grounding resistor as well to that standby generator if the normal power also has a neutral grounding resistor. From there, we can coordinate the system based on the position of the Kirky interlock and make sure that the system is still protected in the event of a ground fault scenario, similar to the scenario it was in when they were in normal power.